Okay. Hello, everyone. My name is Badal Mashadani, and today we'll be talking about the attention is all you need. So, um, what is the motivation behind the transformers? In natural language processing, before the transformers, the recurrent neural network, as just the professor mentioned, were used, such as the LSTM. For the tasks that are relative to text. For example, the tasks of translation. However, due to the fact that is a sequential, it means like it will, in LSTM, for example, it will take word by word, which means it will not proceed to the next word, it will not process the next word until it's done with the previous word. So it goes by order, and that's why it is computationally extensive. So it will take a long time of processing and a lot of computations. So the intuition behind using the transformers, that is, although it's very important to have the order when dealing with texts, however, the transformer is able to do parallelization, which means that it can take all, like if we have a specific sentence, it will take all the words of the sentence at the same time, and each word will have its own path in the encoding, decoding, and so on. And they, of course, since the order matters, we need to know like the position of each word. So the transformer has a way to overcome this issue that I'll be explaining in the next slides. And so back to the other idea behind the transformers, which is the attention mechanism. So what is the attention? The attention in let's say the self-attention means that every word can be expressed in terms of a weighted sum of itself and also on the other words in the sentence, which means the model would look at the other words in the sentence and weigh them to have like the final output vector for each word. So of course, the weight will be dominated probably by the position word itself, but it also will pay attention to the other words, and each word of the sentence will have a specific value that all the weight, of course, for each word will adds up to 1 eventually. So it cannot exceed that. So let's have a high level idea of the transformers. The overview of the model, we can think of it as we have an input. Let's say we'll have like a translation as the example in this paper. So we have the input as a text in a specific language, and we have a black box, which is the transformer, and we have the output, which is the translation in a different language. So what is inside this black box? We have the encoder and we have the decoder. So the encoder, what does it do? It consists of 2 sublayers, which is the self-attention layer and the fully connected layer. So for the encoder, it will receive the input as text, and it's, of course, the computer needs to work with numbers. So the encoder will have the ability to map each word or the sentence into vectors that numbered vectors that represent a specific word. And then it will have the positional encoding, which we'll come to, and thus we'll have a tokens, and these tokens we'll get to that, but however, the encoder will have the output of the encoder will be a vector that will represent each word as the weighted sum of itself and the other words, of the value weighted sum. And the decoder will generate an output sequence for each element at a time. So for the encoder, of course, the output of the encoder will be the input to the decoder, and the transformer use self-stack attention and fully connected layers for both the encoder and decoder. And what we mean by that is that the encoder, for example, it uses, in this paper, it uses 6 encoders that are stacked, which have the same dimension. And the decoder is also composed of 6 layers with a similar dimension. And so first, let's talk about the input of the input. As we said, it will be, okay, the input will be in a form of text, and it will go in the embedding. So what is the embedding? The embedding, we have available like different tables that you can use in your model. For example, word to vector table, and depends on the table that you'll be using. You will have a vector of a specific dimension. Well, for example, we have in this paper 1 by 512, and so each word will be represented by a vector by 1 by 512. Then we have, at this point, we have all the words in random order, and that are represented by vectors. However, we need to know the order of these words because it's important in text translation. So we have something called the positional encoding, and in the positional encoding, there is like an encoding algorithm which we apply. So we add a vector that represent the position, that it will give the model a meaningful idea about the position of each word without influencing the weight. For example, if we have, let's say, a phrase that I am a girl, so the first will be 1, 2, 3, 4. So if we say multiply or add the order to this vector of each word, in this case, it will influence the way, which will change the meaningful of the text. So with the positional encoding, it does not change the meaning of the text. However, it will just give the model an idea, for example, of the distance between the words that are similar or the words that are closer, just giving it a meaningful idea. And in the encoding, we'll have the multi-headed attention, which will come to it now. And of course, we'll add them together and normalize them, and it will forward it to it will be an input for the feed forward layer. Also, we have a normalization layer, and then it will be an input for the decoder. So as we just explained now, the words are embedded, and so after each word is embedded and into a vector, and then applied the positional encoding. So for the even, the first formula is for the even position, and the second is for the odd position. So when the word is at a point that has it was in the position was encoded and it's embedded already, is called a token. So So each token will be in dimension of 1 by 512. And then we'll apply a softmax function to have the output from 0 to 1. Okay. So here we'll explain exactly what is the self-attention. So we have at this point each word in a dimension of 1 by 512. So these tokens will create 3 vectors for each token. And these vectors are the query vector, the key vector, and the value vector, which each one will be in a dimension of 500 by 64. So we'll multiply each token by these 3 matrices, and that these matrices, of course, were trained through the training process, and we'll end up having 3 vectors for each word. So, and each vector, so each vector will have these 3 vectors. Each word will have, each token will have these 3 factors that will be on size of 1 by 64. Then next step is to calculate the score, which is the weight, is by applying the dot product of the query vector with the key vector of each word. So for the first token, for example, we'll multiply the query vector multiplied by the first key and the second key, and so on, like depends on how many words you have in the sentence. And then we'll have the score. Then at this point, the score will divide it by the root, the square root of the dimension of the key vector, which is in this example is 64. So we divide by 8. And then we apply the softmax operation. So we'll end up having a scores that will sum up to 1, like for each token. And then this score will multiply each score by the vector value for each other word, since we already have, like, think of it as a table, for example. We already have the values of the value vectors for the other words, so we just multiply them by the score, and this is to prepare them for the summing part, where we will sum up all the weighted value vectors, and this output will be representing the encoding of a specific token. Then this is like this process is only for like the first token. So this is repeated for all the tokens, and then we'll end up having a table that is called the attention table. So so I explained this for like a single self-attention. So we will have eventually a set of queries, keys, and value vectors that all are backed into a matrices that are Q and K and V. And in this case, as you see, these matrices, like which each one consists like the key vectors, and here like the query vectors, it will have like a matrix multiplication, just same way as I explained earlier. And then here the scaling factor is 1 by 8 as well. And then we apply the softmax, and then we multiply by the value vector. So now we have the multi-head attention. So we already talked about a single self-attention. The multi-head attention is nothing but basically repeating instead of having one key vector, one query vector, one value vector for each token, we'll have 8 of them. So for example, we'll have a 8 encoding for each token instead of one encoding, as we saw earlier. So the multi-head self-attention improve the attention, improve the performance of the attention layer in 2 ways. It will expand the ability to the model ability to focus on different position, and it will give the attention layer multiple representation subspaces. Since we will have multiple sets of query key value weight matrices. So from here, my partner will carry on the presentation. Thank you.
Hello everyone, I'm Shreek Tawal, and I'll continue the presentation from here. So like my partner explained, each sublayer in the encoder and decoder is composed of a multi-headed self-attention layer and also a position-wise feed-forward network. So after the multi-headed self-attention, like two linear layers, where we have the input multiplied by the weight matrix, then we have the bias matrix added up, and then we go through the value activation function, and then again the second layer. So the input and output dimension of this feed-forward network is again 512, which is the overall embedding size in the model, and the inner layer dimension is 2048 for the feed-forward network. So we talked about the attention mechanism in the model. So how are we applying actually the machine model? So like my partner explained, in the encoder decoder attention layers, the queries comes from the previous decoder layer, and the memory keys and values come from the output of the encoder. So this particular mechanism allows every position in the decoder to attend over all the positions in the input sequence. So every position, while translating a particular word or token in a particular position in the decoder, it allows the decoder to attend over all the positions in the input sequence or the input tokens. And also the encoder having the self-attention layers, each position can attend to all the previous positions in the previous layer of the encoder. This is because all the keys, queries, and values come from the same place. That is the input output of the previous layer of the encoder. And similar is the case with the decoder. And the self-attention layers in the decoder allow each position in the decoder to attend over all the positions in the decoder up to and including that position as well. And also to preserve the autoregressive property that the leftward information flow in the decoder is prevented by masking. That is like the decoder cannot know what is coming up next, but it can know, or it has the ability to learn what has come up previously. Like it cannot see the future, but it can see the past. So that is why they do the masking. So this masking out is done by setting the values to negative infinity. So this masking out all the values in the input sequence of the softmax, which correspond to illegal connections. That means the connections to the future are future part of the sequence is cut off by masking out. So why do we use self-attention? What is the advantage of using the self-attention mechanism? So self-attention layer connects all the positions with a constant number of sequentially executed operations. Like we have the number of sequential operations become constant, or O1. Whereas in case of the RNN or a recurrent layer, the number of sequential operations will be ON. This helps in learning the long-range dependencies easily, because in this case, the forward and backward signals have to travel shorter paths in case of the self-attention layer or self-attention mechanism. Also, the self-attention layers are much faster in terms of computational complexity. When the signal length n is smaller than the replication dimensionality d, So the representation unit is the overall embedding size of the model. So when the input sequence length n is much smaller than the representation dimensionality, the computation complexity is much faster. But they also proposed in the paper that for longer sequence, considering only a neighborhood of size r in the input sequence around the respective output position would have a path length of O n by r, which would like increase the computation complexity a little bit, but it will increase the accuracy of the model as well. So like in case of the longer sequence. Also, like my partner explained earlier, in case of self-attention, a number of computations can be parallelized as measured by the minimum number of sequential operations required. So as you can see, in terms of computational complexity and also uh, the sequential operations, in most of the cases, the self-attention layer has a clear advantage over the recurrent layer. And also, as we will see later on, that it also has a higher accuracy. And also here I have just added the table from the actual paper where they have compared the complexity per layer, sequential operations, and maximum path length. So here they have considered self-attention layer, recurrent layer, and the convolution layer, and also the self-attention restricted layer, which is like in the previous slide I explained, like considering only R number of neighborhoods, the size of neighborhoods is R, and the sequence length is N, and representation dimension D, and in case of convolution, the convolution size is K. So as you can see, if the size of n or the sequence length is smaller, this becomes very less compared to the other ones. And also in case of the restricted one, where you consider the neighborhoods, it becomes R and D. So the complexity per layer is smaller in case of the self-attention restricted version in comparison to the recurrent and convolution layer, where they have the D square this term in case of the complexity per layer. Also, in case of the sequential operations, you can see the self-attention convolution and the self-attention restricted version has the constant number of sequential operations, whereas the recurrent network has ON number of sequential operations. Also, the maximum path length is constant in case of the self-attention, whereas they have the ON or O log Kn number of path length. So the self-attention mechanism has much less complexity per layer and much less sequential operations. For the training purpose, in the actual paper, they trained the model on the standard WMT English to German dataset consisting of 4.5 million sentence pairs, and also on the WMT English French dataset consisting of 36 million sentences. So also sentence pairs batched together by approximate sentence length. And they also use the Adam optimizer with the variable learning rate, and they also use some regularization process like residual dropout, where the dropout was applied to the output of each sublayer before being added to the input of the next sublayer, and also they use normalization. Also dropout applied to the sums of the embeddings and positional encodings in both the encoder and the decoder stacks. They also use the level smoothing to increase the Blaze score of the model. So here are the results of which was achieved by the original model. Like you can see, this is the English to German translation task and the English to French translation task. These are the previous models with which they compare in the actual paper. These are the previous translation models. So like you can see, they compare it in terms of Blaze score, which is standard for in translation task. So like you can see, the transformer B achieves the highest Blaze score of 28.4 and 41.8 in case of the English to German and English to France translation respectively. The difference between base model and big model is like in the base model we use smaller number of parameters or hyperparameters, and in the transformer big model they use larger number of hyperparameters. Also, they have compared the training cost in terms of floating point operations per second or flops, where they have also compared it for the English to German and English to French task. As you can see, for the transformer based model, they have the least amount of computations, like 3.3 into 10 to the power 18. So for the other models, you can see they have like 10 to the power 19, 10 to the power 20, where the transformer model only has 3.3 into the power 18, the transformer based model. So the training cost is lower, and also they achieved a higher play score. So it is efficient, and at the same time, it produces better results. They also compared some results with model variation. Like I said earlier, the base model has 6 layers for the encoder decoder. The hidden dimension of the dimensional model of the is 512. The hidden dimension of the feed-forward network is 2048, and they consider 8 heads, and the dimension of the queries keys vectors is 64, and value vector is 64. Also, they use a dropout rate of 0.1 and the level smoothing rate of 0.1. Also, the number of training steps is 100K. And for the big model, as you can see, the hyperparameters are a little larger in case of the big model. Therefore, the big model achieves a higher perplexity score and the Bayes score, as you can see. And they also compare some other hyperparameters. But the big model achieves a higher perplexity score and Bayes score. And although it takes a lot of parameters, as you can see, for the base model, it was 65 multiplied by 10 to the power 6 parameters, where in case of the big model, they have 213 multiplied by 10 to the power 6 parameters. Okay, now let's go to our experimental results. So we actually applied the model on the standard WMT 2014 English-German dataset. We actually used a smaller version of the model. In the actual model, they used like 6 encoder layers and 6 decoder layers, whereas we used three encoder layers and 3 decoder layers. And also we modified some parts of the model, like we used the learned positional encoding using some linear layers instead of the static layers. Like in the actual model, they used the sine and cos positional encoding. And but we used a simple linear layer to learn the positional encoding. Also, we used a static learning rate, whereas they used the variable learning rate in the actual paper. Also, we didn't apply any kind of level smoothing. You can see we achieved a test perplexity score of 5.238, which is better than the actual paper. I think this is because of we use the learned positional encoding instead of the static one. That's why we achieved had better test perplexity score and also a better Bayes score. As you can see, the Bayes score was 26.4, whereas we achieved a 35.38 with a lot smaller model. And so this is this can be pertinent to the use of the learned positional encoding instead of the static one. And also here you can see by our model translation from the German to English sentence. So here is the source sentence, source German sentence. This is the true translation, and this is the translation predicted by our model. So here is you can see it translates almost perfectly, except this young word, like a mother and her young son. Young son enjoying a beautiful day. The model couldn't predict the young word. Other than that, it translates perfectly. And in the right side, you can see the attention matrices, and in the columns, you can see the German words, and in the rows, you can see the English words. So while translating each German word, you can see which, while translating to English, you can see which German word is given attention to while translating it to English. This is for 8 heads. So each head, you can see like these are 8 heads, and for each head, the attention matrix. So you can see while translating this line from German to English A, this head is not giving any attention. So these 4 heads are not giving any attention, but this head, you can see that it is giving attention to this yin word, or this head is giving attention to the yin word while translating it to the English word A. So actually, it is impossible to know before like which head will be used to translate the actual meaning or the actual word. But as you can see, using the multi-head helps the model to learn the representation or get the information from different perspectives, so which helps the model to translate the sentence better. Here is another sentence. Like you can see, it translates the model is was able to translate it perfectly, which matches the target sequence perfectly. And here you can also see the attention matrices of the heads. Here is an example of a longer sentence, as you can see, and the model was capable of translating the longer sentence properly as well. So in this case, you can see the some attention is given to while translating a particular word. Some attention is also given to the other words as well. Like you can see the little bit faint boxes, or lighter boxes are attention given to the other words while translating a particular the word of a particular position. So to conclude this presentation, we can say the transformer model is the first sequence translation model based entirely on attention. So the previous models are translation models are based on recurrent networks or combining RNN with the attention mechanism. But this was the first sequence translation model based entirely on attention. So it replaced the recurrent layers with the multi-headed self-attention layers. And for the translation task, it can be trained significantly faster, like we explained in this presentation, and then recurrent or convolution architectures. And also in terms of performance, it outperforms all the previously reported ensembles, achieving a new state-of-the-art result on the WMT 2014 English to German translation task. And as future work, the authors of the model of the paper told that the model can be extended to problems involving other input modalities like image, audio, video. Like we know that there is vision transformer now, and also local restricted attention mechanism can be investigated for future improvement of the model. So yeah, and here is some references, like this is the actual paper and these are the tutorials from which you could help to build the model. And that's it from us. Thank you.